So we are skipping to section 10.1. Section 9.1 I felt was kind of put in the wrong place, so we've basically moved it to chapter 10. And I will warn you, chapter 10 is fairly confusing.
Oh no.
It's just a tough section.
On a scale
So-
from 1 to 12, how hard is it?
6 being the highest.
Wait, what?
On a scale of 1 to 10, 6 being the highest, how hard is it?
Unicorn.
Oh, wow, that's pretty hard.
Okay, so we're going to talk today about power series. And series is similar to a sequence, but it actually means something different. And it's going to be hard for us to remember that there is a difference between those two words, because they sound almost the same. Sequence series, all starts with an S. We're going to have been doing a lot of stuff, and our brains will be turned to mush, and we'll be like, oh, which one is this again? But our goal is to find if a series converges and represent a series as a function or vice versa. So represent a function as a series. So if we're going to be able to do this, we need to know the difference between a sequence and a series. So we talked about what a sequence was yesterday. What do we mean by a sequence?
List of related numbers.
A list of related numbers. So when we say related, usually we can come up with some sort of function that would give us those numbers. Or, do you guys know the Fibonacci sequence at all?
I've
I've
heard
heard
of it.
of it. Yeah.
The Fibonacci sequence we can define recursively, but we cannot define with a function, as far as I know. That's also something I would like to look up before I make a blanket statement, but most of the time it's defined recursively. It starts with 1, and then it takes the previous two numbers and adds them together to get the next one. So usually the first two terms are 1 and 1. What would the third term be if we add the two together? 2. And then we have 1, 1, 2. I guess I'm going in the wrong direction. So we have 1, 1, 2. So the next term would be 1 plus 2, so it would be 3. Then we'd have 1, 1, 2, 3. So we're adding the 2 and the 3 now, so 5, 8, 13, 21. You're just adding each previous set of numbers. And that one, as far as I know, can't be defined explicitly. We can't find a function for it. But we can define it recursively. So they're still related, but we couldn't actually find a function for it. A series is taking a sequence and adding it together. Let me see how I wrote my definition. The sum of a sequence.
Can you give us an example, please?
Yes, I can.
It's like E and D, if you saw it.
And actually, the sentence I have here will give us an example, so let's go with that instead of doing 2 examples.
Oh, hey, Miss Aiken has a similar example with the turtle.
Okay, so suppose I am walking toward the wall, and the wall is 1 meter away. With every step I take, I walk half the distance left towards the wall. So right now I'm 1 meter away. After I take 1 step, how far away from the wall will I be?
Half a meter.
Half a meter. So sequence-wise, first step, half a meter. Where am I going to be at after I take a second step? A fourth of a meter. How far will I be if I take another step?
An eighth of
An eighth of a meter. Hopefully we're seeing a pattern here. So that is the sequence, my actual location of how far away I am from the wall. But what if I ask you that same question in a different way? What if I don't want to know my location? What if I want to know my total distance traveled? So how far have I traveled after one step? Half a meter. I was 1 meter away from the wall. I'm 1 meter away from the wall. Take one step. I've only traveled half a meter. So after one step, I'm half a meter away. What if I take 5 steps? How would we find my total distance traveled if I've taken 5 steps? Add the first 5 terms together. So 5 steps would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. Yeah, that's 5 steps. I am not going to have us solve that by hand, even though we could. I want you guys to just plug that into your calculator. And then I also want you to find after 20 steps. How far have we traveled after 20 steps? So I'm going to give you a minute or two to solve for after 5 steps and after 20 steps. Good. So 5 steps, easy enough. What did you guys get for 5 steps?
0.96875.
96875, right?
That's
Okay.
like my phone number.
And then probably no one made it all the way to 20, but someone probably made it pretty far. What did you guys get?
I got to 15.
You got to 10? Okay, what'd you get for 10?
0.9999023.
999.023. And then Josh got to 15.
0.999969.
Right. And then 69, but I'm running out of it. Okay, what do we notice pattern-wise of what we've just put in? One step was 0.5.
Bigger.
Bigger,
It converges to 1.
but it's getting closer and closer to 1. Okay. So, even though technically I'd be taking steps forever, I'd still have traveled that entire meter. No, it's a weird concept. But that's the way infinity is. Okay?
Infinity is dumb.
So,
How infinity is
our
insulting.
goal is to find a formula for the pattern
You just can't make it
so we can
smart.
use summation notation to write the infinite series in a more condensed form. So that if I want to find the first 20 steps,
So there's
I don't have to type it in for forever. So in order to do that, we need to find a pattern for the sequence itself. Sequence-wise, what is going on? And I don't want to scroll up so you can see that, but we have the 5 steps here: 1/2, 1/4, 1/8, 1/16. What's going on? How is my set of numbers changing as we take our steps?
Getting smaller.
Smaller. How is it getting smaller?
The bottom is doubling.
The bottom is doubling. So if we're doubling, what are we doing mathematically?
Dividing by
Dividing by 2 or multiplying by 1/2. Do we know information about when we have a series where we're multiplying? That is a geometric series. According to our geometric series, A sub n is a sub 1 times r to the n minus 1. Well, we know all those. What's our first term? 1/2. What's our common ratio? What did we multiply by? every term? 1/2. Now again, we saw something in the warm-up. We could leave it like this, but we could also condense this even further.
You take the
So,
one and
and
then
it
you
would
just
just
put
be-
them together.
1/2.
So 1/2 to the n. So my sequence is 1/2 to the n. My series, we're trying to add all of those terms. So we need a notation that tells us add after you plug in 1, add after you plug in 2, add after you plug in 3, add after you plug in 4. Yep. The series is the sum of a sequence.
I'm just kidding.
We don't have to start at 1. I could change this and say n equals 0 if I wanted. To infinity in this case, because we're doing a series that goes forever. But it could stop. I could say 1 to 20. If I wanted those first 20 steps, I would do the sum from 1 to 20 of 1/2 to the n. Now our calculator will do this for us quite nicely.
Yay!
And I
Yay.
thought I had opened up the program, but apparently not. The program that shows an Inspire up on the screen. So while it's opening, I'll put that back.
Oh, so no, I'm not the.
But I believe if you go under calculus, where most of our stuff is, there should be either a summation button or a series button.
There's a sum.
Summation. And it's, I mean, they make it look exactly like we'd write it, which is very convenient for us. Come on. It's getting slow.
Oh, jeez.
So we can plug that in. When we take a finite amount of these infinite series, we call that a partial sum, which we'll write up in just a second. First, let me, come on.
Is this being recorded?
This,
Yeah, I'm skipping that.
I could pause it, but probably by the time I pause it and then unpause it, we'd be there. Okay, so we need a calculator page. Short. We go to menu, calculus. There is a sum button, number 5. Set up exactly like we write it. So we go n
Your EP is bigger than mine. It's like thin.
equals. I wonder if maybe it's an update issue. Equals 1 to 20, and we have 1/2.
Yeah, you're thinking of me.
Wow.
It will be a
To
cute way.
the
Yes,
n. And we're going to 20.
Your computer's being slow.
It is. So again, like I said, if we do just the fraction,
Yours funny.
that's going to be,
Mine has it as 1.
really, it doesn't,
Wait, did you do?
I wonder if you have it rounding in a different place. Give me a second now.
But you didn't do infinity, Wanda.
Yeah, if you did it to
Oh,
infinity,
yeah.
if you do it to infinity, it's gonna give you 1, because that's what it converges to. Or we could do control enter, and we see, with all the decimals we have shown, 0.999.
Oh,
Off
that's
by
six.
one.
This would be C squared, right?
That's dumb.
So that's the 6. Just wondering.
So, we call these, where we don't do to infinity, but take just one step, we call these the partial sums. And they can form their own sequence. Partial sums, we would take each individually. We'd say, well, what if I just want from 1 to 1? I'm just going to say a sub n, so we don't have to write the function every time, but let's assume we're using that 1/2 to the n function. Well, if I'm only finding the first term, we're finding a sub 1, which is just 1/2. Because we would have plugged in 1/2 to the 1, which is just 1/2. What if I want the second term? Oh, sorry, still a sub n in the summation. That means we're doing a sub n, or a sub 1 plus a sub 2, which is 1/2 to the 1 plus 1/2 to the second, which is 3/4. If we did it to the third, 1 to the 3. So I'm going to skip the middle steps now. I wanted you to get the general idea so we get a little more familiar with the notation. So we do the same thing, a sub 1 plus a sub 2 plus a sub 3, which is really 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3, which would all equal, and we just put it there.
Okay, Mullins is in there too.
Awesome.
Alright, see you guys.
Okay, so I'd add 1/8 to 3/4, which would be 7/8. And as we do that, this time I'm going to use the ellipses going down, saying we keep repeating the same pattern we just did over and over.
So we just keep adding a plus.
So like,
So you
one
just
more,
keep going,
go to
going,
the fourth.
Go,
or go 1 to 5, go 1 to 6, go 1 to 7.
forever.
Yeah, and do that forever. Well, the next one would be 15/16 and 31/32. And if we put those in decimals, we'd see the pattern a little bit better. This was 0.5, 0.75. What is the decimal for 7/8? Thanks.
0.875.
0.875. What about 15/16? 0.9375. I think when we did 31/2, it was 0.9675-ish.
968.
875. That was close. That's pretty good memory. And eventually we got to the point where it's 0.9, 0.99, 0.999, 0.99999. So this itself also converges. So we have three things. We have the sequence itself, 1/2, 1/4, 1/8. We have the series itself, 1/2 plus 1/4 plus 1/8 plus 1/16. And we have a sequence of the partial sums. So it's a lot, especially since we're hearing it for the first time. And when we have it a little more independently, when they're asking us a problem, it's going to be like, well, which one are we talking about? Is it sequence? Is it series? Is it the sequence of the partial sums? There is kind of a lot going on with sequences and series. But something that we can work with a little bit easier is an infinite geometric series. This is a very nice series for us. It will work out well for us. So it takes that geometric sequence, and you notice I put series in red because it's adding it together instead of just listing the numbers. It's taking that geometric sequence where we just listed the numbers, and it's adding them all together. So again, this sum notation is saying plug in 1 wherever you see n, then add what you get when you plug in 2 wherever you see n, then add whatever you get when you see 3. So just again, to practice the notation, you'd have a times r to the 1 minus 1 plus a times r to the 2 minus 1 plus a times r to the 3 minus 1 plus, and then ellipses again saying keep going in that same pattern. And we could simplify that some. If we have r to the 1 minus 1, what is that really?
0 minimum.
R to the 0, which is just 1, so I could write this as a plus a times r, because we don't usually write to the first, plus a times r squared, plus dot dot dot. So this series will converge, but only if it has some certain situations. It will only converge if the absolute value of r is less than 1. We're saying if that common ratio is between -1 and +1. Which makes sense, because that common ratio is what we multiply by every time, and the only way the only way that our next terms are getting smaller is if we multiply by a fraction. And what kind of numbers are between -1 and 1? Fractions. And it only gets smaller if we have a fraction less than 1. If we have a fraction bigger than 1, it still gets bigger. Sorry. I swear I didn't even hit it with my hand, I hit it with my paper.
Hey, it's the 13th.
Weren't we on the next page? Yeah, just went to the bottom. Okay. So it only converges if we're multiplying by that fraction that's smaller than 1. And we actually have a formula for what it converges to. It will converge to a over 1 minus r. They also call this the sum, because it's what you're getting when you add all of these terms together. It will diverge if the absolute value of r is greater than or equal to 1. So we have to be adding smaller and smaller numbers for a series to converge. If we keep adding 0 and 0 over and over again, or something infinitely close to 0 over and over again, it doesn't change the number. But if I add 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, it's going to keep getting bigger, slowly, but it will keep getting bigger. Or 2 plus 4 plus 8 plus 16 plus 32, it's going to get bigger a lot quicker. So let's look at some geometric series. So let's decide if this series converges or diverges. If it converges, I want you to find what it converges to. So I want you to find the sum. I want to know what does this series add up to be. So our requirements, this is a geometric series. We can tell by the formula. And notice this time I used k's instead of n's. K's are also acceptable in summation notation. Sometimes they use j's as well.
Why don't we just stick to one thing?
I have no idea.
Yeah, especially the gym.
So most often we use n's, but j's and k's are also acceptable. And by nature of summation notation, we're assuming integers only. We start at 1 and count up to the next whole number. 1, 2, 3, 4. I could start at 5 and count up to the next whole number, but it's assuming you count up 1 every time. So up here we said when a geometric series converges or when a geometric series diverges. What was that all based off of? R, that common ratio. So where is R located?
It's in the parentheses.
It is the number in the parentheses. So we just want to check, what is 5/3? Is it less than 1 or is it bigger than 1? And actually we need to check the absolute value of 5/3. Okay. This is bigger than 1, it would be 1.6 repeating. I don't know why I rewrite that. It's bigger than 1. So, does it converge or does it diverge? It diverges. If it had converged and I want to find what it adds up to be, we'd plug A and we'd plug R into that summation formula, which in this case I can't do because it doesn't converge, it diverges. So I'm going to have you guys try one.
No, it's gonna converge. What do you bet?
Probably. That is a good bet. So that means you're also going to have to plug it into
Yeah.
the summation formula.
Knew it would be.
Okay, so as you guys guessed, this will converge, but why does it converge?
Because the absolute value of 1/2 is less than 1.
Absolute value of 1/2 is less than 1. And then we had a formula for what it would converge to. A over 1 minus R. Okay, we plug in 3 for A. 1 minus 1/2, which is just really 3 over 1/2, which is 6. So our ultimate goal with this is we're ultimately trying to figure out a way to represent other functions as polynomials. That's our ultimate goal, is figure out what's the polynomial equivalent of this function. Like sine of x, it has a polynomial equivalent. Again, I'd have to look it up. I don't know what it is off the top of my head, but it has something where it's like x plus x squared over 2 plus x to the 4th over 4 plus, it's something similar to that. But there's an actual polynomial that would give us the same function as sine x, because polynomials are really nice to work with. So we're going to experiment here for a minute. We're going to graph 1 over 1 minus x. And we're going to try and find ourselves a polynomial function that matches 1 over 1 minus x from -1 to 1, or matches pretty closely. So at first, you're just going to be kind of guessing. So polynomial, what do I mean by polynomial?
Like
X squared, x cubed, 1/2 x to the 4th minus 5x to the 3rd plus 7. Can be any combinations of x's added together or subtracted. Or both. Okay, so you're going to start by graphing 1 over 1 minus x.
still in the what's it?
Um,
Yeah.
get a new calculator page or hit Doc B if you're in Scratchpad and it'll clear it. Okay, so you're gonna try and pick a second function.
Where?
So I'll just do one at random. X squared minus 3x plus 2. That was not even close. Okay, we're trying our best to find a function that would fit from -1 to +1. So that would go like that, but I only touched that once. If I could drag this around, if it will let me, I don't want to make it bigger. Well, I'm going to go use my mouse. If I could drag it around, I don't want to do the label either. Let me move my graph. There we go. Let my people get it. There. Okay, that's a lot closer than I was before. So I want you to do some guessing and checking and see if you could get close. And it doesn't just have to be x squared. I picked one at random. So I'd hit tab and I'd go back so we don't end up with like 5 billion different ones. And edit this one and see if we can come up with something closer. Something that would get us closer to that function. I'm going to give you 3 to 5 minutes to experiment with that. An even better approximation. Let me get
Emma's is
closer.
pretty good.
Bad.
Not that, just
I don't know if you can beat Emma's.
Hers wasn't even there.
Let's see, we want... I'm going to go back. The smartboard isn't quite sensitive enough for this software
Why do you have a green line across your 4, 5, and 8?
because I drew on it with a smart pen.
That was a pretty stupid thing.
It's not
Uh,
very nice.
Lee. I said to the.
Just kidding. There are.
We'll just go to the 5th. Ah, come on. I hit 5. Okay. Enter.
That's even better than
Is that pretty darn close on the interval we wanted? Okay. So what I did, wrong one, this one, is I said 1 plus x squared, plus x to the 3rd, plus x to the 4th. And if I had plugged in an infinite amount, we would have gotten exactly onto that graph from -1 to 1. So this is actually a geometric series. What am I multiplying by every time?
X.
X. I multiplied, so my common ratio is x. What's my first term? 1. So this is really the geometric, the series, the sequence is 1 times x to the n. The series, we add all of those. Now I'm going to change this because when we're working with this particular series, we want to start at 0. So generally our sequence would be n minus 1, so that when we plug in 1 we get 0. Now we just need x to the n.
Is that 2 different notations? The AN.
Yes, an, I'm assuming I start at 1. We assume sequences start at 1 unless told otherwise. Summation, series, we can tell people where to start, so we don't need to assume. So you know what assuming does. so we found a function, a polynomial function, that matches that function 1 over 1 minus x. But only on a small interval. Where did it actually match it? From -1 to +1. Well, let's think about where a geometric sequence converges. Where does a geometric sequence converge? What interval does it converge on? A divided by 1 over r gives us an exact sum, but what interval? How did we know when a geometric sequence converged? When the absolute value of r was less than 1. So it converged from absolute value of r less than 1. Well, what is r in this case? X. Does that match where it actually matched the function? -1 to 1 is the same thing as absolute value less than 1. Writing it this way instead of this way, sheer laziness. Mathematicians try and make things as easy on themselves as possible. So instead of writing -1 to x to less than 1, -1 less than x less than 1, they're like, I could just put absolute value of x less than 1. Same thing. And we are getting pretty close to the end of class. So let's just talk about what we call this. And then I'm not going to assign any problems on power series yet. We'll just assign problems on what we started with. This chapter, we probably will not make it through one section a day. So I'm going to be stopping at random points in a section because I'm trying to make sure we understand before we move on. It's
Confusing.
yes. Okay, so because that polynomial matches that function 1 over 1 minus x from -1 to 1, we call that summation of x to the n a power series centered at 0. It's centered at 0 because the interval where it was true from was -1 to 1. What's the middle of -1 to +1? 0. So that's why they call it centered at 0. It's because it only matched from -1 to 1. The center of that interval is 0. So they call this a power series centered at 0. And I could, like if I wanted the derivative of this, 1 over 1 minus x, and I wasn't sure what that would be, I could take the derivative of my polynomial. But then I'd have to figure out what is that new summation series going to be as a function. Okay, so homework-wise, page 45.
Get enough taste out of that.
Hey, we have
You're
4
alive!
days.
Alive.
We miss you.